Here are the notes for Unit 7.4, Conservation of Angular Momentum. First, let's talk about what angular momentum is. You may recall what linear momentum is. Linear momentum has the symbol p, it's a vector, and it's equal to mass times velocity, which is also a vector. Angular momentum, we're going to use a different symbol. We're going to use an L for angular momentum. Instead of using mass, we're going to use the rotational version of mass, which is I, or moment of inertia. And instead of using linear speed, we're going to use angular speed. Now, the angular momentum of an object that's rotating is, the direction of the angular momentum is a little bit surprising. It's also a little bit outside the scope of this class, but the angular momentum, L, is actually along the axle or axis of the rotating object. It's something called a cross product, and if you study calculus, you'll learn more about it there. But for now, just know that the angular momentum is equal to the moment of inertia times the angular speed. Remember that moment of inertia for a point is mr squared, and angular speed would be change in angle over change in time. The unit for moment of inertia is kilogram meter squared, and the unit for angular speed is radians per second. Okay, angular momentum is conserved just like linear momentum is conserved. So let's think about a couple of examples. When a figure skater moves her arms in closer to her body while she's spinning, what happens to the skater's angular momentum? Okay, so if we think about a skater with her arms out and she's spinning here versus when she puts her arms in, still spinning, what happens is her moment of inertia, if this is her initial moment of inertia, her final moment of inertia goes down. The reason it goes down is that the average distance from the center of rotation, so the center of rotation would be right down the middle here, that average distance, that center of rotation goes down. And remember that the moment of inertia is the sum of each mass times each radius squared. And so her hands went from a radius about the length of her arms, which might be about a meter, to having a radius close to 0. When that moment of inertia goes down, if this moment of inertia goes down, in order to keep the angular momentum the same, the speed must go up. So when she brings her arms in closer to her body, her speed increases, but her momentum actually stays the same. So angular momentum is conserved just like linear momentum is conserved. So her angular velocity, actually we should use the word speed here. Angular speed increases, but her momentum stays the same. Let's try an example with some numbers. A 65 kilogram student is spinning on a merry-go-round that has a mass of 115 kilograms and a radius of 2 meters. She walks from the edge of the merry-go-round to the center. If the angular speed of the merry-go-round is initially 2 radians per second, what is the angular speed when the student reaches a point 0.5 meters from the center? Okay, let's draw a sketch of this. I'm going to draw a top view. And when I draw my sketches, just like with linear situations, I'm going to draw a before scenario and an after scenario. So here's the merry-go-round, and she's starting at the edge of the merry-go-round. And the radius, it says, her radius is 2 meters. The mass of the merry-go-round is 115 kilograms. The mass of the student is 65. Okay. Let's see. And the initial speed is 2 radians per second. Now, if I want to find the initial or the before angular momentum of this system, I need the moment of inertia and I need the angular speed. I have the angular speed. I have the 2 radians per second. I do need to calculate the moment of inertia. The moment of inertia of the system is additive. So I can just take the moment of inertia of the disk plus the moment of inertia of the student. So the disk is a disk. I can go look that up. It's 1/2 mr squared. And I'm going to treat the person like a point. That's just mr squared. These are 2 different masses. There's a mass for the merry-go-round and a mass for the student. So the moment of inertia of the whole system is going to be 1/2 times 115, that's the merry-go-round, times 2 squared, plus the mass of the student, that's 65, times 2 squared. So my initial moment of inertia of the system, I'm getting out my trusty calculator here, is 1/2 115 times 2 squared plus 1/2 65. Oops, I forgot that. Oh no, this is just a point. There's no 1/2 there. 65 times 2 squared. So I get 490 kilogram meters squared. I'm going to use Notability to cheat a little bit here and clean this up. Okay, so the angular momentum of the system initially is 490 kilogram meters. Ooh, I keep writing kilogram meters per second. I'm thinking of linear. Kilogram meter squared times the speed. The speed was 2 radians per second. I'll multiply that together, and the initial angular momentum is 980. The units for this are still kilogram meters per second. Okay, next I'm going to think about what happens after. Now it says that after, or she's going to move, so she moves from the edge here to a point 0.5 meters from the center. So the moment of inertia is going to change. I'm going to give myself a little more room. So the new moment of inertia is going to be the moment of inertia of the disk again, plus the moment of inertia of the student, but the radius of the student is changing. So I'm going to have 1/2 mr squared. Oh my goodness. Let me zoom in and do a better job here. Plus mr squared. This was 1/2 times 115 times 2 squared. Okay, so now for her radius has changed. So now it's 0.5 meters squared. So the final moment of inertia, let's see what we get here. Just making sure it matches. Okay. So the new moment of inertia is 246.25 kilogram meters squared. So if the angular momentum does not change, So that if the angular momentum is still 980 from over here, now I can solve for the final speed. Oops, I'm going to put in 246.25, and I'm going to solve for that final speed. And I get that the final speed is 3.98 radians per second. So when she goes toward the center, so again, she walked toward the center, and the speed went from 2 radians per second. Oops, I thought that was the highlighter. Let me try that again. The speed went from 2 radians per second, there we go, to 3.98 radians per second. So the merry-go-round speeds up. Okay, well, if we can use conservation of angular momentum, we also can apply the impulse momentum theorem. So you may recall, again, this is more review, that momentum in the linear sense, this is all linear stuff, this is review, is a vector. Momentum equals mass times velocity. And last time we learned about how the, if you take Newton's second law and you write it in terms of the definition of acceleration, then, and we multiply both sides by t, we get this thing, called the impulse momentum theorem. And the left side is called impulse, and the right side is change in momentum. We can do the same thing for a rotating system. We can say that the change in angular momentum is equal to the torque times the change in time. Remember that net force, when we go to a rotating system, net force is the same thing as net torque. Remember that mass is the same thing, or is analogous to moment of inertia. Time stays the same across different scenarios, so that's nice. And momentum, linear momentum, is analogous to angular momentum. So when I look at a graph like this one here, where I've got torque and time, that tells me that the area, if I take torque times time, the area is going to equal the impulse, and it's also going to equal the change in angular momentum. So let's look at this question. In an experiment, a student applies a net force to the edge of a disk for 10 seconds. The students may change the magnitude and the direction of the force at any time in the experiment. A graph of the net torque exerted on the edge of the disk as a function of time is shown. After observing the graph, the student concludes that the angular momentum of the disk has not changed. Does the graph support the student's conclusion? Justify your answer. So I would say, no. I would say that this does not support the student's conclusion. I would say that the angular momentum has changed because the impulse, which again is torque, net torque times delta t, is not 0. In fact, if we wanted to, we could figure out how much it changes by figuring out the area. Let's look at one more example. These are from the College Board AP classroom topic questions. A disc-shaped platform has a known rotational inertia ID. Okay, so this rotational inertia is another way of saying moment of inertia. And again, they're using the symbol I, so hopefully we remember that. For a disk, I is 1/2 mr squared. The platform is mounted on a fixed axle and rotates in a horizontal plane with an initial angular velocity, omega d, in the counterclockwise direction as shown. After an unknown time interval, Okay, so delta t is unknown. That's good to know. The disk comes to rest. A single point on the disk revolves around the center axle hundreds of times before the disk comes to rest. Frictional forces are considered to be constant. A student must determine the angular impulse that frictional forces exert on the disk from the moment it rotates with angular velocity in the counterclockwise direction until it stops. What additional data, if any, should the student collect to determine the angular impulse on the disk? Justify your selection. Okay, so let's go back up to what impulse is here. So we know that impulse is equal to change in momentum. Oops, that didn't work. Let me try that again. There we go. So this side of the equation, the torque times delta t, that's our impulse. Now, let's see. One way to think about this is to think about, one way to get the impulse would be to get the change in momentum. And in this case, the shape is staying the same, so the moment of inertia is the same, and the angular speed is changing. So, let's see. We have the initial angular velocity. We know that the final angular velocity is going to be 0 because this thing is coming to rest. And we also have the moment of inertia. They gave it to us here. So actually, it looks like we can figure out the impulse because we can figure out the change in, we know the moment of inertia and we know the change in speed, and that will give us the change in momentum. And the change in momentum will give us the impulse. So we don't need any more data. In fact, the change in momentum, which again is equal to the impulse, is going to be equal to the moment of inertia times the change in speed of the disk, which is basically going to be omega d. So that's it. All right, thanks.